In this video, we're going to do some guided exam question practice on the 2003 chemistry question and higher level paper that came up on shapes of molecules and polarity of molecules. Now, I'm just counting up the marks here. I see that altogether, I think we had a total of 36 marks. So this is a good portion of a full question. You're approximately 12 to 15 minutes here, I'd say, is your timing, because you're not quite a full question for 20 minutes, but you're 2/3 of it, if you like. Now, to get all the marks here, you actually don't need to write very much, okay? So you could finish this really quickly. If you know your stuff, you're going to do this in 3 or 4 minutes. But you do have to be very careful. You have to know your stuff, but there's quite a lot of details you could miss in this question, okay? And it could leave you not getting some of the marks because you've missed the details. So let's just be careful. All right, so the first thing is a definition, straight up definition, and it's electronegativity. So without explaining anything more to you at this stage, you know what your definitions are, you've got to learn them. I've explained them in full detail, but now you've got to do the learning and make sure they're in your long-term memory. So electronegativity, pause the video and write down the definition there now. Okay, so what you should have written here is electronegativity. What is it? It's the relative attraction. Relative attraction. An atom has for the shared pair of electrons in a covalent bond. Okay, so we've done that loads of times. Relative attraction, and that has for shared pair of electrons, covalent bond. Very, very quickly again, just recap the idea. Here's a bond, HCl. Here is the shared pair of electrons being shared between the chlorine and the hydrogen. And the idea here is that they are not quite shared equally. Okay, so if I was to redraw the shared pair of electrons as being on the bond, if you like, both atoms are going to attract the electrons towards themselves. But the fact is that the chlorine has a much higher nuclear charge, and therefore, because it's got more protons in its nucleus, and therefore it's going to have a bigger pull on the electrons than the hydrogen. So the arrows here represent pull on the shared pair of electrons by each atom, and the chlorine is higher because it's got a higher nuclear charge. And that means it's got higher electronegativity. So chlorine's electronegativity, En, electronegativity, is bigger, and hydrogen's is smaller. Okay, right. So that's the big idea of electronegativity again. All right, the next one, describe using dot and cross diagrams. So you have to use a diagram, guys, because it says describe using, you've no option here. Okay, the bonding in the water molecule. So water, as you all know, is H2O. Okay, and really all you need to do here is draw the final structure, describe it. You could have a little bullet point explanation on the side. I think that's always a good idea, but it's water. So what I want to do is pause the video. We use a dot and cross diagram to show the bonding in water. Is it covalent? Is it ionic? You guys need to know that. And then a quick bullet point explanation down the side here. Okay, pause the video and do this now. All right, so the first thing you should have done is drawn the oxygen. And the oxygen is a central atom here. And there are 2 hydrogen atoms attached. Let's first of all figure out how it's going to be. Oxygen has 6 valence electrons, it's in group 6. And it's going to share 1 pair with each of the hydrogens like this. So here is the hydrogen's 1 electron, this dot here, and it's sharing it in a pair with the oxygen. So there is how that works. So each of these bonds represents a shared pair. This should not be new for any of us. And then oxygen has 2 other lone pairs. Now, if you count them up at the end, you should count 6 valence electrons on the oxygen. Here they are. There's 2, there's another one, and there's another one. 6 valence electrons still there, but it's got a share of this pair, and it's got a share of this pair. So count the number of pairs. There's 1 pair, 2 pairs, 3 pairs, and 4 pairs. So the oxygen is satisfied. Each hydrogen is satisfied. They've got a share of a pair. So that is how that works. Now that's really all you needed to do to get the full marks here. Actually, is you just needed to draw that bonding. Okay, so how would you explain it? Oxygen shares a pair of electrons with each hydrogen oxygen has 2 lone pairs, and each atom at the end, why do they do it? Each atom has a stable electron configuration. That's why they do it, to get a stable electron configuration. So oxygen has 8 in its outer shell now because it's got a share of 8, and each hydrogen has 2 in their outer shell. They've each got a share of 2. That's why it happens. Right, next question. What is the shape of the water molecule? Now, I nearly missed that. I nearly went straight to reading this, and this is why I said the important thing is in the detail. So the first thing here is, what is the shape of the water molecule? So next question is shape. Pause the video, write down the shape. Right, you guys should know that this shape here is what we call V-shaped. It's a V-shaped molecule or a bent molecule. Definitely not linear, V-shaped or it's bent. Right, that was it. Next one. Which of the following, 104, 107, 109, 120, or 180, would you expect to be the closest to the bond angle in the water molecule? Explain your answer. So look, there's 12 marks going for this section. There was 3 going for this. So there's 9 going for this part. So it's really important that you don't miss the detail here. This explain your answer is actually worth, what, 3 of the marks? No, 6 of the marks. So this is actually worth 6 of the marks, and people could miss that really easily. Okay, so which bond angle is the closest out of these bond angle? Is the closest, so out of these options. So pause the video and choose which bond angle is closest. And this question is a little bit annoying because none of those are the exact bond angle that we learned about in class. But it's not asking what's the exact bond angle, it's asking which one is closest and why. So we're okay with that. It's not saying which one of these is the right one. So bond angle, hopefully the one that you went for was 104. Now in class, we would have learned 104.5 was the proper bond angle. So this one here is definitely the closest, 104. And explain your answer. This is the important bit. Why is it this one? Why is it this bond angle? What causes the bond angle of 104 when we look at this up here? So pause the video and write down the reason why this is the correct bond angle. All right, so what you should have talked about here, looking at the structure, is it's kind of like a tetrahedral. It's like a tetrahedral because tetrahedrals have 4 pairs of electrons around them. A classic tetrahedral is this, CH4, like this. CH4. Carbon has 4 pairs of electrons around it, but in this case, it's 4 bond pairs. 4 bond pairs. Okay, each electron around it is in a bond pair. So each line represents a bond. This is the same in that the oxygen has 4 pairs of electrons around it, but it's different because they're not 4 bond pairs. So if you didn't talk about that, I want you to use that to explain why this here is the bond angle, 104.5. Pause the video, do that now. All right, so why is this the correct bond angle? Well, oxygen, the oxygen in water has 2 lone pairs and 2 bond pairs. Oxygen has 2 lone pairs and 2 bond pairs. Okay, now, what do we know about the strength of repulsion between lone pairs and bond pairs? How is these extra lone pairs here going to reduce the bond angle? The bond angle for this is 109.5 on a tetrahedral. So why are we saying it's 104 in this case? Pause the video and write that down now. Okay, so we say lone pair repulsion is greater than bond pair repulsion. This is something we learned about earlier. And what do we know about that then? We know that the two lone pairs on oxygen push the bonds closer together. So together. Showing this up here, what we're saying is that these lone pairs are pushing these bond pairs a bit downwards. squeezing them together. This squeezes them a little bit together here. All right, so instead of being 109.5, nope, it's now 104.5. So we say that every lone pair of electrons makes a difference of around 2.5 degrees. So you could take 2.5 degrees away from the original bond angle of 109.5 for each lone pair. So we've got two lone pairs, so take away 2.5 and then take away 2.5, and that will give you 104.5. So that's the difference, and that's the explanation. So the bond angle is reduced at the end here. So the bond angle is reduced. Okay, so it's easy marks if you know it, but you just have to be careful not to miss the detail. That was what 6 marks here, this explanation. And if you missed it or you wrote something really scatty there, you're not going to get them marks. All right, so you could think you're doing really well, and it might not. You might not be hitting the nail on the head. Right, let's look at the next bit on to part C. The diagram on the right shows a thin stream of water flowing from a burette. So we saw this experiment in class. What would you expect to observe if the charged rod was brought close to the thin stream of water? So if you brought a charged rod, say this rod here is carrying electrons on it, negative charges, what would we expect to happen to the thin stream of water, and why? Okay, so this is part C, and charged rod. So the charged rod experiment, what would we expect to see, and explain why? So if you wanted to, you could draw a diagram of it, no problem, or you could just explain. Pause the video and do this now. All right, so guys, if you were drawing a diagram, you draw something like this. Here's your burette. Here's your burette. Here is your water, and we're going to draw it deflected towards the charged rod. So this here is your charged rod, and we call this movement or this bending, we call this a deflection. And it deflects towards the charged rod. Why is this? This is because the water organizes itself, its molecules, where it has its delta positive charges towards the negatively charged rod. And that's why they move towards it. Now, this wasn't part of the question, but just in case, I want to make you aware of what happens is sometimes they say, what would happen if you replace the rod with a positively charged rod? And some people think that it would do the opposite, that it would bend away from the rod, so that the stream would actually go like this then. But that's not what happens. It still deflects towards the rod, so it still does the exact same thing as over here. Why? Well, the water molecules now reverse their order so that the delta negative side is pointing towards the charged rod, and therefore it still attracts, still flex towards the rod. That's just a side issue. So what do we expect to see here? So writing it down in a couple of bullet points if you don't have it already, describing bullet points what happens. Pause the video and do that now. All right, so you probably really only need one bullet point here. Just exactly what do you see? Water is deflected, is a good word to use here, deflected towards the charged rod. Now, other words you might have used here is attracted. Water is attracted towards the charged rod or bends towards the charged rod. That's fine. All right, the next part is to explain why does this happen? Why does it happen with water? What's the story here? So pause the video and write down why it happens. All right, so the crux of the story here is it happens because water has dipoles. Water has dipoles. Or you could say that water is polar. And the dipoles are attracted to the charged rod. Now, thinking about this is an extra question again. What would happen if we had a non-polar substance, a substance without dipoles? What would happen there? All right, so I'm triggering your mind, well, if there's no dipoles, then there's nothing to attract to the charged rod. Then what we should see is just the stream just continues straight down, undeflected, because there's nothing in there, positive or negative ends, to be attracted towards the rod. So if it was a non-polar substance, so if it was non-polar without dipoles, you get no attraction. If it's polar, you get an attraction. All right, guys, so that is that question. It was 36 marks. I'm just going to leave you with the marks so you can have a look. check your answers again, make sure that your language is correct and that we're okay on that. And that's it, guys. So I'll see you in the next video.